Hey, my name is Sid,
And I'm Belize.
and Salvin is doing something very, very important right now.
He is in Coachella.
4 hours. No one likes you, Windows Update. What are we doing today, Belize?
We're doing SVD, or singular value decomposition.
Awesome. So, for someone who has no idea of the SVD, how would you describe it?
You're decomposing a matrix to its orthonormal vectors and singular values.
Okay, so let's start with the real case. Let's say you have a random matrix, not random matrix, that's something
And
else.
it doesn't have to be symmetric.
Exactly. Say you're starting with an arbitrary matrix A, which is an m by n matrix. We can break this down into three matrices: U, sigma, and V transpose. But when Belize said we broke it down into the orthonormal vectors, that's because there's an alternate form of writing the SVD, which is saying that A is going to be equal to the sum from I is equal to 1 to R, where R is the rank of the matrix, times sigma I, Ui, Vi transpose. And we'll make the connection between this and this soon. So, Belize, before we look into the orthonormal vectors, what are some properties of the singular values?
First of all, singular values have to be all non-negative.
Okay. So sigma I is going to be greater than or equal to 0 for all I.
And they're also real.
They're also real. Interesting. We'll get into more why this is later.
All right.
Cool. And now, the reason why we would like to break a matrix into this form is because this allows us to better understand the structure of a matrix. Okay, so let's get into why we like this particular form, like why the singular value decomposition is useful to us.
Okay.
So what can you tell me about V1, V2, V3, Vr that might make it useful for us? And why particularly this transpose is kind of useful for us?
Right. First of all, as we said in the beginning, all the v's are going to be orthonormal.
Mm-hmm.
And when we multiply it with a vector, then we're actually taking the inner product of v and the vector we're multiplying.
Exactly. And another way of putting it is, since these form an orthonormal set, like if you were to change our bases in some sense, I'm using the word change of basis loosely because we only have like R vectors, so it may not be completely the full basis. If you were to look at an arbitrary vector x within this subspace, we can see the representation of that x within the subspace as x is going to be x v1 times v1 plus x v2 times v2 plus x vr times vr.
Yeah, and like the only reason you can write the coefficients as the inner products is again because they're orthonormal vectors.
Bingo. Cool. Now, let's say we have an arbitrary vector in this form, how does the SVD help me understand the output of such a vector x into? So like, why would this form be beneficial when looking at A times x?
I think I know where you're getting at. It has to be something about inner products being 0 for orthonormal vectors.
Cool, exactly. So because of linearity, A times x is going to be A times the sum of this whole thing, Vi times Vi, I is equal to 1 to R. Because of linearity, we can bring the A inside, which is equal to the sum of I is equal to 1 to n, x times Vi, where this is just a number, times AVI. Cool.
Yep.
Now what's AVI? Why is that useful for us?
Well, okay, if we just look at our matrix representation for A, if we right multiply the whole thing with Vi, then we're going to see some of the terms are going to go to 0. Actually, most of them.
Exactly. So A times Vi is going to be the sum from I is equal to 1 to R times sigma I, Ui, Vi transpose. Okay, let me change the index to J.
Yeah, that's going to be easier to see.
J times Vi. So what's this going to be?
Well, it's going to be 0 except for the case when I is equal to j, right?
Because
they're orthonormal.
bingo. So this whole thing becomes sigma I ui, and I don't know why I said it in a tone that suggests there's something more, but that's exactly it.
But that's it. That's going to be it.
Pity. So AVI is sigma I ui. So you can put that in here, and then we get A times X is equal to the sum of I is equal to 1 to N, or R. My N's and R's look really similar. I bet no one else has that problem. Sigma I times ui.
My 9s look like G's, so that's okay.
Your what? Your 9s?
Yeah, it's sad.
How do you do that? Wait, can you write your 9?
My 9 is like this, and my G is like that.
Your 9s look like Q's more than G's.
Yeah, it's a shame.
Can you write your Q before you raise it?
Fine. Oh my god.
Caught on
My
camera.
students know this problem, I'm sure.
I'm sorry for your students. Luckily, I don't think that we use index Q that much in 16B.
Yeah.
Cool. Okay,
All right,
so now
this looks useful.
yeah. So now let's try and connect this form of the SVD to this form. So like when studying this form, we've like so far used this form to understand what happens to an arbitrary vector AX. Now we'll see why we might sometimes want to look at this form instead. Cool.
Okay, before you move on, we can also say that like we could have multiplied the expression with UI transpose and get the whole thing in terms of the singular value and
Sure.
VI transpose.
Yeah, you can do, if you look at A transpose, this is going to be the sum from I is equal to 1 to R times sigma I VI UI transpose. And then the same thing holds, but slightly flipped. So A transpose UI is going to be sigma I VI.
Right. Sounds
Cool.
good.
So this is like a cool way of showing that, I mean, if you assume the SVD exists, this is a cool way of showing that the row rank is equal to the column rank. Actually, we should talk about that before we move on. So here we've just said the sum from I is equal to 1 to R of sigma I. And these sigma I in this form are assumed to be non-zero.
Right.
And this kind of gives us the rank of the matrix. And we'll discuss this a little more when we explain the transition from this form to this form.
And
But
it's only non-zero because we're summing up to the rank, right?
exactly.
Yeah.
So basically, if you do the singular value decomposition, the number of non-zero singular values is the rank of your matrix. And your singular values don't really change when you look at A or A transpose. So that's like a quick way of remembering that the row rank is equal to the column rank.
Right. And that comes from the fact that UIVIT is a form called dyad, and they're rank 1 matrices. So
Yeah.
you're essentially summing a bunch of rank 1 matrices.
That's true. So UIVI is a rank 1 matrix. And then if you're summing R of them, you get a rank R matrix because they all happen to be orthogonal to each other.
Mm-hmm.
Cool. Both of us really like linear algebra, so this is really cool for us. Okay, so let's explain how this form, sigma I UI VI transpose, I is equal to 1 to R, can be captured in this form and why this form might be a little more useful sometimes. This is the form that we mostly get when we look at
The Python?
when you look at MATLAB or Python. This is the form that you usually get.
It's really easy. You just do SVD, and then it just gives you the whole thing in IPython.
Pretty much.
Technology.
The one thing that kind of annoys me though is MATLAB, when you call SVD, you get USV as your return value. And in Python, when you call SVD, you get USV transpose. And when you study the complex case, we'll understand that we have to conjugate it too.
Yeah.
But it's kind of annoying. It's like, it's as arbitrary as the 0 index and the 1 index difference.
Well, MATLAB sucks, right? So it's fine.
Sure, that also works. Okay, please. I'm going to write this out really big.
So that solvent can see.
all the way from Coachella. Okay.
You won't be sober enough. It's okay.
I'm sorry, Salvin. Okay. So the reason why I wrote U sigma V transpose like this is because we're going to study how to relate this to this, where this is U is going to be an M by M matrix, this is going to be an N by N matrix, and this is going to be an M times N matrix. And this is U sigma V transpose.
All right.
Okay, Belize. How would you, let's start with this matrix.
Okay.
What would you put along the diagonal? And we'll explain why it's in a diagonal soon enough.
Right, so you're going to put the singular values on the diagonal, and the convention is that you have to put them in the decreasing order.
Okay, so let's assume sigma 1 greater than sigma 2, greater than sigma 3, and so on, greater than or equal to sigma r. And then we're going to do sigma r plus 1, sigma r plus 2, and so on.
Right.
What are these values going to be?
They're all going to be 0.
Exactly, because now we've already captured the rank of the matrix.
Mm-hmm.
So here's sigma 1, sigma 2, sigma 3, dot, 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 sigma r. And this part kind of tends to confuse people, but after we have the rank of the matrix, we're just going to pad the rest with zeros.
Sounds good.
Even if this is going to be, if you look at the transpose, so like sigma transpose, it's going to look like this. It'll still be like sigma 1, sigma 2, dot, dot, sigma r, and then pad with zeros, and everything else will be a 0.
Perfect, yeah.
Cool. So we have that A times VI is going to be sigma I UI. Right? So if I were to put VI here, V1, what would the V matrix need to be so that, like if I were to do the inner product, like kind of like this times this, what would need to be in this row?
Well, it would need to be V1, right?
Whoops, goddamn technology. This would be V1 transpose. Exactly. What would be the one below that?
Yeah, it's going to be in the decreasing order, so it would be V2 transpose.
Bingo. And let's just go to VR for now. VR transpose. Dot, 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 dot.
And that's actually what IPython returns when you call SVD. It gives you the largest vector and largest singular value for index 0.
So because these are orthonormal, when you do V1, if you do this matrix times V1, so if I look at V transpose times V1, I'm going to get 1, 0, 0, 0, 0, 0. If I look at V transpose times V2, I'm going to get 0, 1, 0, 0, 0, and so on. But what do we do? We want an n by n matrix. So what do we do with the remaining sections, remaining rows?
Well, it's going to be similar to what we did for the sigma matrix, right? So we need to like pad it with something somehow, but
yeah, but
it's not going to be 0.
It's not going to be 0, exactly. So the reason why we kind of look at U and V transpose is we kind of saw how it was useful to look at V1, V2, and VR all the way till VR as like an orthonormal set that's standard subspace. So now we're just going to extend that to be a basis of everything in the input space. So
Exactly.
if I look at A as an M by N matrix, A is a function that takes an n-dimensional vector to an m-dimensional vector. So if you're looking at Rn, maybe we want to complete the basis for Rn.
Exactly. So we just need to find other orthonormal vectors to the set of for V.
Quick question, why orthonormal?
Well, for the whole set, or
Why can't we just fill these vectors with arbitrary vectors to complete the basis? I was just going for because we can.
Okay.
Roughly speaking, we just want to complete it with orthonormal vectors because it's really convenient. And as we said, if you look at X in terms of orthonormal vectors, it's easy to get the decomposition with orthonormal vectors.
Right.
That's all I was going for. I'm
Okay.
really bad at asking questions. I apologize. So how would we get orthonormal vectors for the remaining space?
We could do Gram-Schmidt.
Exactly. We can just use Gram-Schmidt. So let's just assume we have like E1, E2, E3, all the way till En, and then you can do Gram-Schmidt to figure out what the other orthonormal vectors are. Or you can, like, if you have a simple enough matrix, you can most of the time just look and figure out what is something that's going to be orthonormal to it
By inspection.
by inspection. So let's just assume we've now filled VR plus 1, VR plus 2, and so on with orthonormal sets. The reason why it doesn't really matter which orthonormal vectors we use is because the corresponding singular values are 0.
It's going to be 0.
So if you look at A times VR plus 1, it's going to be 0 times something. It doesn't really matter because
Exactly.
you're multiplying it with 0.
It's a little bit easier to see in the dyadic sum form
Yeah.
because its coefficient is going to be 0. So
Exactly. It kind of captures the fact that VI, since you're only summing till R, and we are multiplying other orthonormal vectors to it, that is not from, like we're doing multiplying this thing with VR plus 1, R plus 2, because of orthogonality, it's just going to be 0.
perfect.
Cool. And now,
We just
complete the
need to
U
fill
matrix.
it. Yeah.
Yeah, how would that look like?
Yep. So if we just like inspect a summation, then we can see that the first singular value should correspond to U1. So I guess we would put U1 as the first column.
Cool. So this would be U1, then continuing the pattern, this would be U2.
I feel like a student who sits in the front row.
That's a very good point. I didn't think about it like that. That's pretty cool. So you have U1, U2, dot, 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 UR. And again, by Gram-Schmidt, because it doesn't really matter, we do UR plus 1, UR plus 2, and so on. Now, what was I going to say? If I remember what I was going to say, I'm going to keep this in the video.
All right. Fill this with some joke about Savin.
Do you know about Bob?
Which one?
No, not Bob the person, Bob the clown. When we did
Oh.
the observability matrix, we call it OB. Then Savin called it OB, and then
Okay.
I put a smiley face here because it looked like an inverted smiley face. And then when he wrote it down this side, it kind of looked like a killer clown. So that's how Bob became a killer clown.
Cool story.
I wish it was cool. I personally really wanted it to become a meme, but I think everyone was really creeped out. It was like during the time when
Please, someone make a meme. Makes it happy. He makes all these videos for you.
you can make Billy's the new Bob. Okay, I don't remember what I was going to say, so I'm just going to move on.
All right.
Actually, no, I do remember what I was going to say. So, if you want to find the rank of the null space,
Okay.
how would we do that given the SVD matrix?
That's a good question. So first of all, we need to remember the rank nullity theorem, right? How it works.
Okay, so like your dimension of your, so the rank nullity theorem, or as most people call it, the fundamental theorem of linear algebra. I hate the rank nullity theorem, like the way it's in. If you have like a linear function that takes an n-dimensional space to an m-dimensional space, you have n, which is this, is going to be the
The rank
dimension
of your null space.
or rank of your null space. So null of A plus the dimension of the range of A.
Which is also called the rank of A, right?
Or the rank of A, exactly. This is true. Rank of A.
All right.
Cool. So what is the rank of A?
Well, it's R because we defined it, right?
Yeah, okay. This is the rank R, which means that n minus R is equal to the dimension of the null space of A. Now, another way of thinking about it is, let's see. If you were to look at Rn, it's going to be in this. It's going to be like in the span of these basis vectors v1, v2, dot 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 vr times vr plus 1 dot 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 vn, right? And now the null space of A are all the vectors. Like, so the null space is defined as the set of x in Rn such that A times x is equal to 0.
Right.
right? So given that we have a basis form of it, and we know that these three vectors, these R vectors, are not, these three vectors get sent to sigma I ui, which is not equal to 0. These vectors are the sort of like the basis vectors in Rn that get set to 0,
Right.
which means that these basis vectors sort of span the null space of A.
Exactly.
And then the dimension is the number of linearly independent basis
Which is
vectors,
going to be n minus r.
which is the same thing as n minus r, which is another way of thinking about it.
That's cool. So it's, again, like easier to see if you just like look at the summation form and remember
Exactly.
if like the only case where you get a non-zero thing is the case where I equals to j, and since we're summing up to r, we're never going to have r plus 1 or n, right? So they're all going to go to 0.
Exactly. Yeah, cool. Now, what's the dimension of the what's the basis for the range of A?
Well, in this case, I guess like it's easy to see, right? Because it's going to be the u. Is it true? Yeah. The u vectors
The U vectors up to what point?
up to r.
Up to R, exactly. Because everything else in this space never actually gets reached. Because everything in the output, A times Vi, is going to be sigma I ui. The Vi kind of captures everything in the input space. And the only thing that you ever reach in the output is going to be some form of ui, where I is going to be from 1 to R. So your output space is completely characterized by your U vectors from 1 to R.
Yeah, also like another way to see it is like if you, again, look at your summation, you can see that when you are multiplying with an x, I transpose x is just taking an inner product, which is just a scalar, and the singular value is also a scalar, and the only vectors you have are u's. So
Bingo.
yeah, that's going to be your range.
As you can clearly see, Belize is completely partial towards this sum. Okay, cool. And now we're going to talk about why, when to find an SVD, we look at A transpose A or A transpose.
Cool, sounds exciting.
Awesome. So for now, let's just assume the SVD exists, which it does, but the proof is kind of out of scope. So like A is equal to U sigma V transpose.
All right.
Right. Believe, what does A transpose A look like in terms with respect to the SVD?
Well, first of all, we need to remember that A B transpose is B transpose A transpose.
Awesome.
Okay, so since we have the SVD, we can figure out what A transpose is. All right. So in that case, A transpose, following the formula, is going to be V sigma U transpose.
Sigma transpose.
Well, sigma transpose, but I guess we're gonna hand wave that part a little
We're
bit.
gonna hand wave that part. Exactly. So if sigma is to like, let's just, people are making noise, sorry about that. If sigma is like sigma 1, sigma 2.
Corey is busy
dot,
on
dot.
Sundays, unfortunately.
Yeah. If sigma is like that, for example, sigma transpose would look like sigma 1, sigma 2, like almost identical, except that now the 0 is over this side.
All right.
Cool.
Oh no.
Technology. How many East majors does it take to use a Wacom tablet properly?
It's
2.
tough.
Okay, Belize, what does, so if you're looking at A transpose A, this is going to be equal to V sigma U transpose times U sigma V transpose.
All right.
What is U transpose U?
Oh, since we have orthonormal vectors, it's going to be identity.
Exactly. So to just illustrate that, you have U1, U2 times transpose times U1, U2, and so on, which is going to be equal to like a matrix of inner products. So like U1, U1, U2, U2, U1, U2, and so on. By orthonormality, anything outside this is going to be 0. And by the normality part, all these become 1. So it just looks like the identity matrix. So this is going to be equal to V sigma transpose sigma times V transpose. What does sigma
Okay.
transpose sigma look like? Just like expand it in terms of this.
Well, we're going to have the square terms on the diagonal now for
Mhm.
singular values. Then everything else is going to be 0.
Yeah. So
And
now
also it's going to be a square matrix.
it is going to be a square matrix because like if sigma was m by n, sigma transpose would be n by m, and then
Perfect.
you'd have an n by n matrix. And then you'd have sigma 1 squared, sigma 2 squared, sigma r squared, and zeros on the
Perfect.
other part. So now this kind of looks like V times some diagonal matrix times V transpose, where this
Mhm.
lambda looks like this. What does this look like where you have like, so first what is, V is orthonormal, right?
Right.
So what is V transpose with respect to the inverse of V?
Well, it's going to be the same. V transpose is going to be V inverse.
Exactly. So like V transpose times V is equal to I because of the same orthonormality conditions. And if you kind of like compare it to P D P inverse, this kind of looks like the eigenvalue decomposition.
Oh, that's right.
Yeah, exactly. So we studied a theorem called the spectral theorem, which basically says like assuming you can have complex eigenvalues, if you have a symmetric matrix or a Hermitian matrix, which is basically saying if you take a random matrix T, take its transpose, and then conjugate every entry, which we use. Let me use a dash for conjugate.
Okay.
So this means like I take the transpose of a matrix and take the complex conjugate of any entry. If that is equal to T itself, then T is a Hermitian / self-adjoint matrix. There's so many names for it because it's so useful.
But for real matrices, like, only thing you need to know is if the matrix is equal to its transpose, then you
Yeah.
can call it a symmetric matrix.
Exactly. So the T transpose conjugate has two shorthands. One is called TH for
And
Hermitian,
T star.
and T star. That kind of like captures the self-adjoint aspect of it because mathematicians and engineers diverged a while ago, and now they've sort of converged again, and now we just agreed on two notations.
All right.
I don't know what to do about it. Getting rid of some stuff. So what the complex spectral theorem tells us is that if you have a self-adjoint matrix, so if T adjoint Hermitian is equal to T, you're guaranteed to be able to find an eigenvalue decomposition, VD V Hermitian,
Right.
where D is going to be a diagonal matrix consisting of the eigenvalues,
Mm-hmm.
and V forms a complete basis. And not only does it form a complete basis of eigenvectors, the bases are also guaranteed to be orthonormal, which is
Yeah.
super useful.
What he means by complete is it's going to have n dimensions, essentially. If you're working
Exactly.
with n-dimensional matrix, then you're going to have n orthonormal basis vectors.
Exactly. And so if you look at this thing, and this is in the real case, if you look at A transpose A transpose, this is going to be equal to A transpose, A transpose A.
Mm-hmm.
So you take the eigenvalue decomposition, you get something that looks like this, where it'll be V, some matrix whose columns consist of orthonormal eigenvectors, a diagonal matrix consisting of the eigenvalues, and the inverse, which in this case is just the transpose of the matrix.
Mm-hmm.
And that's exactly what we use to get this. And we've shown how it's related to the SVD, in that the eigenvalues are basically the squares of the singular values.
Right. And also, you know, sums are my favorite, so you can express this as a sum. So you can say,
Let's go to a new page.
Okay.
Yeah.
All right. So you can say T was V, D, V Hermitian, right?
Mhm.
So we can say T is sum of VI, VI transpose, right?
Mm-hmm.
Right. And where lambda i's are eigenvalues.
Mm-hmm. Exactly. And this also, one thing of the complex spectral theorem that I forgot to mention is that the eigenvalues that you get are guaranteed to be real
And
as well.
non-negative.
And non-negative, yes. And then that's why when you look at the square root of the eigenvalues, you get sigma I, and the sigma
Mhm.
I is completely well defined.
Perfect.
Cool. So that is why whenever we want to calculate the SVD of a matrix A, we look at A transpose A to get V lambda square lambda V transpose, or we look at A transpose to get U lambda U transpose, where the only difference between these two lambdas is that the dimensions are different and the extra
Right.
parts would be padded with zeros.
Hmm. And we know that we can relate U's and V's with the formula that we derived earlier, which
Yeah.
was A VI is equal to sigma I UI.
If you're ever trying to get the full matrix form, we'd use Gram-Schmidt to complete the basis.
Right, exactly.
Cool. Now let's do one of the most important applications of SVD.
Oh, also, one thing to mention is the vectors in U are called the left singular vectors, and
Yeah.
V's are right singular vectors, just by
Yeah.
definition.
So A is equal to U sigma V transpose. These are the left. These are the right.
Yep.
Cool.
Perfect. Does it matter which one I use, AA transpose or ATA?
That's a good question. So say like your matrix is R times M times N, where M is greater than N, right?
Mhm.
So now if you look at A transpose A, this is going to be an N by N matrix,
Right.
right? And this means you're going to do a smaller eigenvalue
Which is
decomposition. But that also means you have to do Gram-Schmidt to
More.
find the remaining vectors in U if you want that.
Mhm.
If you don't need to use that, this is almost definitely better since you've solved a smaller problem. But if you don't want to do Gram-Schmidt, you can do AAT and get the eigenvectors and then calculate the remaining singular vectors, AAT to get the left singular vectors, and from AVI is equal to sigma I UI, you can calculate the remaining right singular vectors.
Right.
Yeah. And this is advantageous because we don't necessarily have to do Gram-Schmidt unless a particular lambda I is 0.
Mm-hmm. Cool.
Cool. I personally like doing the smaller eigenvalue problem because after some practice, it's pretty easy to guess eigenvectors, guess vectors that are orthonormal to a certain set of vectors. And most of the time, the questions we ask you will have simple forms that are simple to guess. So like, what's the vector that's orthogonal to 1, 1, 1, minus 1? What's a vector orthogonal to 1, 0, 0, 1, and so on.
Yeah, that's true.
Cool. So now let's talk about everyone's favorite topic, PCA, or hashtag machine learning, hashtag legit science, hashtag linear neural network.
Oh, wow. What about deep learning?
Hashtag deep learning with linearity.
Yeah, that's what Sid does in his free time, just generate hashtags about machine learning.
It's just funny because a lot of the EE professors kind of implicitly bash on machine learning. Because most of the, I don't want to say most of the concepts because I'm not super versed in machine learning, but from what I've seen of it, a lot of it is very closely related to statistical signal processing. So it's just funny.
That's fair, yeah.
Yeah. Note. Side note. Okay. I've kind
Steve would have loved that.
Steve, you mean Steve Connolly?
Yeah.
She does research with Steve Connolly. Cool. Blaze, why don't you lead us into PCA? What's the problem statement?
All right, so PCA is principal component analysis. So as we said, we have R principal directions if we have a rank R matrix, and we're trying to determine what's the most important singular value that we have in the sum.
What do you mean by R principal directions?
Right, so if we have, a lot of data and we want to see that maximum variance of the data for us to better understand or interpret the data, then we choose a direction in which we will have the most variation.
Explain max variance.
Right.
I'm going to progressively break it down.
All right. So when we choose a direction, depending on the mean values, then we're going to project our data and then figure out how far each data point is from the mean. And when we sum that, then we're going to have a large variation if it's large. So the direction that we're projecting onto is going to be our principal direction.
Okay. So roughly speaking, if this is your data, and let's assume it has a mean of 0, if you pick this particular direction, like arbitrarily, the distance from this direction does not really capture
The variation in the data.
it doesn't really capture these points too well. So if you were to pretend each one consisted, so if you were to look at this point, for example, it has one of this component. I guess it has something that looks like this and something that looks like this. And if I just had this direction, I would be only able to capture a small part of this data point, which means that if I were to look at the error would be pretty large.
That's true,
right?
yeah.
Because kind of like this whole distance is not captured well. And so when you say maximum variance, we're basically saying if you were to look at all the data points and look at this direction and subtract the errors from trying to estimate this point with this direction, we would get a really large variance or a really large error. Cool.
That's fair, yeah.
And what PC is trying to do is to find the first best direction that best minimizes the max variance in some sense. So it kind of like explains the biggest variance in the
Sure,
sense
yeah.
that it.
So in discussion, if you're into discussion, we had an example of stock markets. So the principal direction would be kind of like the average case that explains the variation of the stock
Exactly.
market the best. So if you only looked at those stocks, you would have a pretty decent idea of like how the stock market is doing. So that average is going to be your principal direction in this case.
So if these are like your data points, kind of like the overall trend, guessing it kind of looks like this. I guess actually a little kink over here. And that, sure. I kind of wish I didn't draw that. So we're basically trying to find a direction such that like minus a scalar in this direction, kind of like the distance from this is minimized. So the error is minimized.
Sure, yeah.
And that's what you mean by explaining the best variance, because you're trying to reduce that error. And then the next principal component is once you have the best direction and like you've accounted for that, what's the next best direction? So like if I have a vector that looks like this, and I have one basis here and one basis here, this kind of explains the vector the best. But after I remove this component, the next best thing that explains this component is going to be this part. And that's what the second singular vector would do in some sense.
Right. In the two-dimensional case, it looks kind of stupid, but if you like, increase the dimensionality to like 100, then this actually makes more sense, right?
Yeah. I hope that was okay in terms of if you play a drinking game, please do not do something that's related to the number of times you said variance in this part, because
that would be bad.
that would be bad.
That would be bad. Okay.
Okay. How would we go about this? What is like why exactly does the SVD roughly work? Like why does the SVD help in figuring out the principal components?
Right. So essentially what SVD does is it decomposes the matrix into its orthonormal bases, right, which are the singular vectors. So since we have those, then we can actually figure out so again, like we can write our, oops, that is an eraser. From where sigma I, ui, vi transpose, right? So essentially what we want is the sigma. Again, like sigmas are in the descending order up to sigma r. And we're trying to find sigma 1 because that's going to explain most of the sum, right? And in that case, we can, if sigma 1 is big enough, then we can say this is almost equal to sigma 1. Wow, that was bad. Okay, let me.
Don't go to the blue box. That's where faces are going to be.
Sad. Okay. So we're trying to find a sigma 1, U1, and V1 transpose that explains most of the matrix, essentially.
Yeah.
Right. And U1 is going to be your principal direction in this case.
That's a little misleading. So it really depends on how we arrange the data. So if you have...
yeah, if you put your data into columns, then it's
Exactly.
different from putting into your
Exactly.
rows.
So like the simplest example I can do to explain that is if you're doing like trying to find the principal face. So this is the face of one person, this is the face of another person, this is the face of another person, and so on, right? So one way is if I make this a vector, I can make this into this row, make this form another row, this form another row, that form another row, and so on, in which case we have a matrix that looks like this. In this case, all my faces are rows, so if I want to find the principal direction, I kind of want to find the principal row.
Right, in that
So
case
in
it's
this
different.
case, I'd want to look at the V matrix.
That's right, yeah.
If I put this as a column, so this is a column, this is another column, this is another column, column, and so on. In this case, I want to look at U.
That's right, yeah.
Cool. And the only other thing that we really need to worry about when doing PCA is kind of the demeaning thing, which is not really, it's not,
Intrinsic to what PCA is trying to accomplish, but it's more like a step that you do to
yeah.
work with the data in an easier way.
It's, yeah. Let me just finish erasing this, because for some reason I can't erase and talk at the same time. So if you had data that looked kind of like a cloud in this area, I'm just going to like color it in. If you have a cloud in this area, but all of them have like a mean offset, so like they're all offset by this value. If I'm trying to best explain this data, this offset, whoops, whoa.
Yeah, that offset means nothing, so you kind of just like get rid of that while like doing your
Yeah.
scoring.
This offset kind of like would, if I do PCA on this data, the biggest thing that I'd first try and represent would be somehow captured by this offset. And we don't really want that because we're trying to find principal directions that separate the data from each other, not necessarily from like some arbitrary 0 point. So we then shift our coordinates by subtracting the mean into looking like this, and then we get the two principal components.
Right.
Cool. All right. Thank you for watching.
Thank you.
Thank you, Billy, for replacing Savin.
It was a pleasure. Hopefully we didn't make Savin too mad.